Okay guys, so we'll be discussing a small question before proceeding. So let's say we have 2 moles of an ideal gas which is heated from 300 Kelvin to 400 Kelvin. Okay, and heat supplied is 10 kilocalorie. You have to calculate the this is at constant pressure, let's say at constant pressure. So you have to calculate change in internal energy. Okay, so there are two ways of approaching it. We know that delta H would be equals to delta U plus delta PV, or rather it is the heat exchange at constant pressure, so we can write it is at P delta V, or another one is delta U is equals to Q at constant pressure plus W. Okay, so why can we write it like this? Because heat exchange at constant pressure would be equals to change in enthalpy, so we can write it as 10 into 10 to the power 3, which is 10 kilocalorie. We are just converting it into calorie, so it would be delta U plus what would be P delta V. So as it is an ideal gas, we can write that PV equals to nRT, and as if we take the delta on both the sides, then we can write delta PV would be equals to delta nRT, and it is at constant pressure, so we can write P delta V would be equals to nR delta T. So just put the value of nR delta T here. Delta T is 100, you know the value of R, you know the value of N, 2 moles. Delta U can be calculated from the same. I'll leave the calculation part up to you. Okay, next let us start with a new concept, which is the concept of work. Okay, so if we talk about PV work, then PV work is either expansion or compression. Okay, so that would be P delta V. And if we talk about gravitational work, then it would be mgh. M is the mass, G is the gravity, and H is the height. If we talk about electric work, it would be N Fe, or V times I times time. Okay, and N is the number of moles of electrons involved in cell reaction. Okay, and E is the EMF of the cell. We'll be discussing more on this, so you can leave this topic for now. We'll be discussing more on this chapter in the coming lectures. And 1 Faraday is equals to 96500 coulomb. Okay, so these are all the types of work which are there in the physical nature, and specifically we'll be talking about PV work as a part of the this chapter, which is thermodynamics. Okay, so now let's discuss on the limitations of first law of thermodynamics. Limitations of first law of thermodynamics. Okay, so first point is that our first question is the complete conversion of heat into work possible? Of heat into work possible. Second point is Is a particular reaction or process feasible? Is a particular reaction or process feasible? Third point is, to what extent does a reaction proceed? So these are all the points which the first law of thermodynamics is not able to answer. To what extent does a reaction proceed? Fourth point is, first law of thermodynamics is unable to provide answerable answer to all these questions, so it's not particularly a point. So just a note that all the above points is not answered by first law of thermodynamics. Okay, so here comes the second law of thermodynamics. Okay, which says that complete conversion of heat into work is not possible. Heat into work is not possible. Is not should be in bolds and capitals. Not possible. Oops. Second point is that heat engine is based on Carnot cycle used to convert heat into work. We'll see what Carnot cycle is. This Carnot cycle is in the coming lectures. So heat engine is based on Carnot cycle, which is used to convert heat into work. Okay, so we have high temperature here. Okay, high temperature body at temperature T2, which gives heat to the heat engine. Heat engine does some work and then supplies rest energy Q1 heat energy to a lower temperature body at T1 temperature. Okay, so percentage N, or the efficiency of the Carnot engine or the heat engine, would be T2 minus T1 divided by T2 times 100. Okay, and that should be equals to Q2 minus Q1 divided by Q2 into 100. Okay, and efficiency would be between 0 to 1. Okay, so with this we come to the end of this lecture. In the next lecture we'll be continuing on seeing more on work. So till then, good luck and goodbye.